Welcome to Module 15 group presentation, everyone. So, my name is Miguel Gutierrez. I will be the audio and presenter for this presentation, as well as Biuld Gonzalez. He will do his part on ethical analysis. And I'll be also taking care of Eleazar Garza's presentation as well. So, this is by Eleazar Garza, me, myself, Miguel Gutierrez, and Biuld Gonzalez Lopez for this presentation. Let's start. Introduction to Therac 25. The Therac 25 was an advanced radiation therapy device that was designed to treat cancer patients with high precision and minimal pain. Unfortunately, it took different approaches, resulting in severe accidents caused by software bugs and design flaws led to multiple injuries and fatalities. This case highlights ethical issues in engineering. Therefore, we will provide an overview of Therac 25, analyze the ethical challenges, and propose solutions to prevent horrible tragedies. Case study overview. According to Charles Huff, during the 1970s, AECL Atomic Energy of Canada Limited and a French company CGR were developing prototypes, Therac 6 and Therac 20, which they were the first two versions that used software manually. However, after AECL ended their work with CGR in 1981, in 1983, they introduced their advanced computer-controlled medical machine as a software operation, combining these two versions into one machine, Therac 25. Now, Therac 25 relied heavily on software for safety purposes, and it was to target on cancerous flesh from patients to destroy it with an X-ray beam. However, the machine presented flaws that resulted in massive overdoses of radiation, leading to severe injuries and deaths. Nevertheless, the FDA, Food and Drug Administration, were aware of the situation, so they implemented AECL to tackle the situation as quick as possible to avoid incidents in the future. However, the FDA were dissatisfied with their progress due to being slow and inadequate response, resulting to shut down the operation. I want to give you guys the timeline of the Therac 25. Since you guys know about 1970s and 1981 and 83 a little bit, we want to go more in depth about 1985 to 1988. So, what happened was on July 26, 1985, a 40-year-old cancer patient, Donna Gardner, was getting her cancer treatment from Therac 25 at Ontario Cancer Foundation Clinic in Hamilton, Ontario, Canada. During the session, the medical machine shut down 5 times with an H-tilt error, indicating no doses was delivered, causing her the burning and stinging sensation. 3 days later, she returned and was hospitalized for radiation overexposure, making the clinic to report the first victim to AECL. This made AECL to investigate and implement safety redesigns to prevent situations. Unfortunately, she passed away on November 3, 1985 from cancer, contributing to severe radiation damage. 1986. So, during 1986, there were 3 patients who dealt with Therac 25 from East Texas Cancer Center, ETCC, Tyler, Texas. Bonnie Ray Cox, Isaac Dahl, and Daniel McCarthy. They went through severe radiation overdose from the back with sickness, neck and shoulder, and face, respectively. Now, Isaac Dahl and Daniel McCarthy experienced a machine error that the medical staff accidentally pressed the up arrow key, delivering a massive overdose of radiation, malfunction 54. AECL were notified and advised removing the up arrow key as a temporary fix. Unfortunately, these 3 patients passed away suffering from radiation overdose both in August and May of 1986, respectively. FDA requests more information from AECL, which AECL filed a correction action plan, known as CAP, to undergo through the situation. Now, I want to take you guys to the simulation of Therac 25, how it was operated. So, this simulation of Therac 25 is demonstrated in Spanish, creating malfunction 54 from AJZH2074 from Wikimedia Commons. Now, what he's doing is that, the operator follows the direction that the patient is prescribed to have and to set up the position of the machine, which he's doing right now. When you see the actual one, those are the actual specs that is supposed to be prescribed for that machine and the patient. And in a bit, so after everything doing it right, when changing from X as an X-ray beam to E, which is going to happen right now, as an electro beam, and commanding B to begin, malfunction 54 in English, or file 54 in Spanish will appear. 1987. On January 17, 1987, 2 patients, Anders Engman and Glenn A. Dodd, were undergoing the radiation treatment from Therac 25 at Yakima Valley Memorial Hospital. In Engman's perspective, the medical machine was shut down and secretly gave Anders a burning sensation and developed strip skin burns. AECL was able to discover the flaw that he received massive overdose of radiation, approximately 8,000 to 10,000 rads, when he was supposed to be prescribed 86 rads. For Glenn A. Dodd, he suffered overdose during treatment. According to Ethics Unwrapped, on February 6, 1987, the FDA notifies AECL that the machine is defective and let the operators know not to utilize it until improved. As a result, they both died on April 8, 1987 from radiation overdose, leaving AECL to finalize their reports and tests, which they have been insufficient to keep their records updated, which will be the last resort for 1980 in 1988. So, according to Charles Huff, on January 28 to November 3rd, 1988, AECO has issued an interim safety analysis and released the final safety analysis reports, concluding their investigation and corrective actions for the Therac 25, respectively. This means that they have identified to fix or improve the flaws, while still investigating and testing the machines. This led to making a final report from 1985 to 1987, analyzing the failures and changes to the hardware, software, or operational protocols. Nevertheless, the hospitals were hesitant to utilize their equipment and find alternative solutions. I will pass it down to Biuld Gonzalez Lopez. He's going to do ethical analysis.
Hello, my name is Biuld Gonzalez Lopez and I'm going to present ethical analysis. The Therac 25 case illustrates significant ethical failures, inadequate software testing, poor communication and transparency, unclear accountability, and flawed interface design. Responsibility for software failures. AECL engineers mistakenly rely heavily on software for safety features in the Therac 25, ignoring the importance of hardware backups like interlocks, because they act as physical backups in case the software doesn't work properly. This led to harmful radiation overdoses due to software errors. This decision created a situation where one problem could cause everything to fail, removing a significant safety measure for patients. In addition, their decision went against industry best practices, which emphasized the need for various safety systems to lower risks. The lack of attention highlights the importance of attentive methods and the implementation of multiple safety measures. 2. Failure in communication and transparency. ACL didn't communicate well with the hospital staff and operators regarding to the dangers of Therac 25. Error messages such as malfunction 54 didn't provide helpful details about how serious the issue was, leaving users uncertain about critical safety risks. Their slow response made problems worse and violated the ethical duty to communicate clearly on time. The lack of clear error report made it hard for operators to address fixing problems. For example, the unclear messages didn't show the difference between a small problem and serious failures, making it hard for operators to understand how serious the situation was. 3. Lack of clear accountability. The blame for the problem with Therac 25 was shared between different groups such as AECL, hospitals, and operators. AECL said that the users were not operating the machines correctly, while the operators believed that the machines was dependable, causing more confusion. This spread of responsibility led to a negative cycle where no one felt motivated to tackle the main cause of the problem. Hospitals trusted AECL's claims about the machines being safe. However, AECLs pointed to mistakes made by users and how in hospitals operations causing accidents. Additionally, the rules for checking medical devices fatigued because they were not good standards for software systems at the time. And 4. Poor design of the interface. The machine's interface was difficult to understand and didn't provide visual information to the operators. Hence, the error messages were unclear. The operators didn't receive enough training on how to deal with them. These design problems made it more difficult for operators to see and stop dangerous situations which directly led to accidents. A bad design example is when there are no safety measures to stop operators from moving forward without fixing mistakes. For example, the interface let users overlook important problems without warning about what could happen in the end. Depending on the confusing errors caused, like malfunction 54, can make it complicated for operators. They had to figure out what the problem was and how serious it was, but the issues were made worse by not having convenience to use, like clear layouts or visual signals, which could have helped operators to spot and fix problems quickly. Thank you.
Hello again, it's me, Miguel. I will be presenting proposed solutions, which I want to give a shout out to Eleazar Garza, who has been doing the slides. So, there are 4 solutions that could have been successful if the Therac 25 was not a failure. Solution 1: effective communication. Effective communication could have played a crucial role in preventing the disasters and errors from Therac 25, whether within the workplace, between an operator and a device, or from a device to a team. Clear communication is vital. In this case, improving communication from Therac 25 operator to the rest of the team, as well as from the actual device itself to the operator, could have prevented confusion and injuries. Let's move on to solution 2, if it moves. There you go. So solution 2 is corrected testing procedures. Another solution proposed would have been testing the design flaws and correcting any errors presented upon who was conducting the tests. The Therac 25 was tested by the FDA for errors and safety purposes, which it did pass and was then granted approval to market the device. However, there were some factors of the software that were not taken entirely into consideration during the process, since it was based on the previous Therac 6 and Therac 20 models. Such factors included occasional errors that were brushed off as interference from electromagnetic noise. Solution 3, if it moves, there you go. Okay. So solution 3 is credible supervisors. The third proposed solution correlates closely to the second solution mentioned previously. It is about having certified or professional engineers at the site to test and detect any flaws in the design of the software or coding rather than overlooking the problem entirely. Keeping credible or professional engineers in charge of testing procedures can make sure that everything works correctly and logically. And last but not least, solution 4. If it starts, there you go. And this will be documentation. The fourth proposed solution would be to have everything documented and reported. While one of the procedures were documented, such as the testing and safety analysis, there were errors that were not considered carefully, which led to the failure of Therac 25. Like the previous solution regarding effective testing, making sure to include all factors, having credible professionals and engineers approve of the device, not just FDA, and document everything in accordance with what the professionals detect, can lead to the Therac 25 to success. And that is all for proposed solutions. And I want to take you all to this video, which is right there in front of you. So in this video, YouTube video from Kyle Hill, he will explain about the history of Therac 25 in depth and how it has affected the engineering field, visualizing and understanding the errors it caused patients to not get treated properly at their local hospital or clinic as it was supposed to be in the first place without problems. So you can check it out. We'll probably leave it in the description below if you guys want to check it out. It's just in depth about it. So to conclude this, the Therac 25 case highlights the devastating consequences that could have been prevented if AECL have not released the device to the market, believing they had sufficient protocols. This serves as a thoughtful reminder of the ethical responsibility that engineers must prioritize in their designs, ensuring safety and reliability. By learning the lessons from these failures, we can prevent future tragedies and ensure that technology is used responsibly and ethically. And to give credit, I want to give credit to Eleazar Garza, to myself, and Biuld Gonzalez Lopez for doing our part for doing this presentation. So I want to thank you all for doing that. And there's a bunch of references, so all that. So thank you guys for listening to our presentation, and hope you have a great day.